Thank you for joining this session. I'm Sara, a platform engineer. I'm here today to talk about topology-aware scheduling in Kubernetes. By the end of this session, I want you to have a clear mental model on where the current setup fails, how DRA changed the interface, and leave with some reusable patterns that you can apply to your workloads, regardless of which accelerators you are running. So why topology blindness causes invisible performance collapses in Kubernetes? I want to start with a question. How many of you have deployed Kubernetes workloads, like a training job, distributed inference server, high throughput storage pipeline, or any other workload that allocates multiple accelerators and got inconsistent performance or way worse than bare metal without any obvious reasons? One? From Kubernetes perspective, everything is okay. The pods are running, no errors, no alerts, limits are satisfied. Kubernetes seems calm, but the benchmark number is just wrong. You may spend days debugging this issue. It's more common than people admit. It has a name and there is a fix. So the structure is always the same. When a workload needs physical resources that needs to be physically close, one bad placement can break the hardware fast path silently, which means that at the workload level, no sign of errors, no sign of warnings, just the system keeps running but slowly. And it's very hard to debug. Let's take a few examples. For example, here we have GPU plus RDMA NICs. In this scenario, for distributed disaggregated inference scenarios, for example, placing these two devices in different hardware segments disable the fast path between them and the bandwidth drops. For GPU to GPU communication in some of the distributed jobs, placing these two devices in different hardware grouping drops the throughputs because the communication goes from the fast path to the slow path via a different hardware path. And for example, the third example is about CPU and any other accelerator. Also for these two devices, placing them in different hardware domains add latency to every memory access between a device and host. So the key point here is that you don't need to run any of these specific workloads. The pattern is generic. Any two devices that needs to communicate fast, split apart, that's bad placement, and that's topology blindness, and it's the scheduler fault. So Kubernetes scheduler plays workloads in a way that violates hardware performance model. Because Kubernetes does not have any understanding or understanding of the device collocation requirements, it had no way to know it does this. Kubernetes knows, for example, that a node has specific number of resources available, but nothing about their topology. The result is workloads are running perfectly from Kubernetes point of view, but perform poorly. So the performance here is determined at the pod bind time, not when the workload is running, but when the scheduler itself made the placement decision. And no fact after this can recover a bad placement. So the core issue here is that Kubernetes treats all the resources as flat resources, but the hardware reality is different. Servers are hierarchical systems. So let's try to understand the hardware reality. In the modern servers, every device sits somewhere in a hierarchy. At the top level, we have the CPU sockets on its local memory and PCIe root complex. The root complex connects different devices, and devices like GPUs, NICs, or storage devices, etc., can communicate directly under the same root without involving CPU, without involving any memory copy, and that's the fast path. Crossing to the other socket means that the data needs to travel through the interconnect socket link, and that has a real cost. Bandwidth drops and latency increase. And workloads continue running without any sign, but the system performs poorly and very slowly. And this is hard to debug and detect. So this is what we call topology cliff. It's not a gradual curve, it's like a step function. Same hardware, same cluster, but complete different behaviors depend on which side of the boundary your devices lands on. And this is like the hierarchy is real, and the boundaries are hard, but Kubernetes scheduler does not understand any of it. And this is the exact issue that we need to solve. If we ignore this structure, the performance will stay unpredictable. So what close means for different device pairs. For example, for GPU plus NIC, close means that they are collocated in the same, under the same PCIe root. This enable the fast path between them, and devices can access directly each other. If we place them apart, this means that the fast path will fall back to the slow path, and the throughput will degrade. The bandwidth will degrade. GPU, like communication between two GPUs in the same distributed job is like close in this scenario means that the GPUs are in the same NVLink island. Placing GPUs in different islands it breaks the performance. It does not matter how GPUs are close within the PCIe topology. If they are belonging to different islands, NVLink islands, the all collective or operations falls back to the PCIe path. So the closeness here is not a single concept; it's hardware specific, and it has each pair of devices has its own proximity boundary, and the Kubernetes scheduler needs to know all of this, but currently it does not know any of it. So why Kubernetes is topology blind? To understand why the topology is completely invisible for Kubernetes, we need to understand how Kubernetes makes or scheduler makes its own placement decisions. So the scheduler relies on device plugin interface. The device plugin is the daemon set sitting in each one of the nodes. Each one of the nodes, and reporting to the kubelet the number of resources available per node, which means that it reports counters to represent the availability of different resources. That's all. No hardware description, nothing about the topology, just counters and integers. And when when a pod or a workload requests resources, for example here, 2 GPUs and 1 NIC, or DMA NIC, the scheduler will select a node that has enough token counters to satisfy this request, place the pod, and start it, without any consideration of the hardware topology, any consideration of collocation requirements between these devices, which means that the requests are treated independently. 2 GPUs means 2 GPU slots available somewhere in the node, and 1 NIC available somewhere, without any understanding of relationship between devices. And we could end up with different allocation patterns that are not consistent, which means that, for example, in this scenario, GPUs can land in the first socket and the NIC in the second one, which means that the communication between GPUs and NICs needs to cross the the inter-socket link, and this has a real cost. The scheduler without topology can still make like locally correct decisions, but it's still globally incorrect. And this is because Kubernetes has been designed to run workloads that are CPU bound, where the resources are independent, and network topology is that rarely matters. But running AI workloads today, modern workloads today, means that all these assumptions are violated. And but the Kubernetes schedulers still keep allocating or scheduling scheduling workloads based on no topology, no consideration of device collocation requirements. And from the outside, for example, this looks like a network issue, but in reality, it's like a scheduling issue. But what we really need to say here or to express is, give me two GPUs that are in the same PCIe root with the NIC. And this sentence does not have any representation in the device plugin semantics today. The Kubernetes scheduler still picks one of the node with valid counters, plus place the pod there, and that's it. That's the entire decision loop for at the scheduler level. And this is not a bug. This is how Kubernetes and the device plugin has been designed. The topology was not their scope. But today, with modern workloads, topology is what we need. So let me skip this to optimize some time. So teams today to try to reach out for like quick workarounds to fix this kind of these issues, topology issues. One of them is to pin some of the device lists in at the container level, bring the topology at the container level, etc. But all these fixes fails because they are bound to specific nodes. If we change the node model or we change the representation of devices in the node, this cannot work. And the big issue here is that we are trying to recover or to fix an issue that has been created at scheduling time in the wrong place. This is the wrong layer for the fix. Another strategy to fix this issue is to use the device plugin with topology manager, and this approach works in two disconnected phases. The first phase still the Kubernetes schedulers picks the node based on counters, available resources somewhere in this node, and then bound the pod. And when the pod is bounded to the node, the kubelet kicks in and starts gathering some more topology informations to find the right NUMA node, for example, to place the pod. If there is no available node for this to satisfy the requests, the pod can get rejected, and it requires a scheduling or rescheduling from scratch. And this retry loop is the real problem here. The topology manager and device plugin are making placement decision or topology decisions at admission time. After the scheduler has already picked a node that is not satisfying the request with like incomplete informations. And now the kubelet needs to undo this. For simple like workloads, this can still work, but if you are running complex workloads where multiple accelerators needs to work together and they are sensitive to topology, this will break. So to solve this issue, we need scheduling decisions to be part of the or to understand the hardware topology. DRA brings this, the hardware topology as a scheduling constraint. This is the fix, like the right fix at the right layer. Topology-aware scheduling means that the Kubernetes, the scheduler itself needs to think about physical location or collocation of devices, not just about their availability. And the enabling the technology for this in Kubernetes is DRA, Dynamic Resource Allocation. This allows the scheduler to reason about the resources with their attributes, for example, PCIe root locality, NUMA nodes, bandwidth capacity, etc., before scheduling them. So the Kubernetes new API DRA, which is generally available in Kubernetes 1.34, is fundamentally changing how the contracts between hardware devices and the scheduler. Before DRA, device plugin publishes integers to express resources per node. With DRA, the drivers or hardware drivers are publishing a structured inventory where each device is represented by a named object with typed attributes. So the scheduler now can read this inventory, evaluate your constraints, and place the pod in a node that satisfies these requirements. This eliminates the problem at admission time rejection because DRA is bringing the topology at scheduling time. So DRA itself is a set of APIs, Kubernetes controllers, kubelet plugins, and hardware drivers. So the drivers for specific hardwares publish the inventory with the characteristics of the different devices via the resource slice. This is the per node inventory for each device, and a device class that represents the type of device that we are publishing here. And this can also be created by your cluster administrator. Think of it like the storage class, but for compute. On the other side, the user can express the requirements of device allocation and the collocation the constraints between the different devices via resource claim templates and resource claims. The resource claim template is the template that the user creates once, and the Kubernetes controller will create per pod replica resource claim to bind the resources to specific pod in a specific node, which means that the Kubernetes scheduler reads the inventory published by the driver, evaluates the constraints and the requirements for allocation from the user side, and picks the right node that will satisfy the request. Then the kubelet kicks on and start the device allocation at the container level. So this is the whole model. This is the approach. Topology now is visible to the scheduler, and we can make right decisions based on the full picture that is available in the different resource slices. One important thing about DRA is that the driver don't need any coordination between each other. So for example, the GPU driver written by or developed by a GPU vendor, NIC, driver by a NIC vendor, and any other custom driver that you can write. They don't need to know about the existence of each other. They don't talk to each other directly. But since they are talking all to the same Kubernetes API, with a single simple claim, we can compose a hardware profile with combining different devices from the set of drivers that we are publishing for each node and enforcing some collocation requirements between them. And this gets evaluated at the scheduler level, not at the driver's level. So this allows the users to create any combination of multiple drivers and bring them all together in a single request that is created and expressed by the user via resource claim or resource claim templates. What kind of devices you need to compose for your workload is very specific to your use case, and you need to think of what is the right device composition that you need to provide for your workload to work. Let's take a deep dive or like a zoom a bit on the resource slice itself. So instead of saying this node, for example, has X number of GPUs and NICs, the resource slice is describing the different devices via specific attributes. The two GPUs are belonging to different NUMA nodes. They are in different PCIe routes. The NIC itself has RDMA capability enabled. It's sharing the same PCIe route as the first GPU. So, which means that this topology now is available to the scheduler. It can read it, understand it, and reason about it. On the other hand, the user or the user in general can express the allocation pattern or intent via a very expressive resource. Here we have the resource claim template that has two big sections. The first one is the requests, how many devices we need for our workload and which type of devices we need. And for example, here we have two GPUs from the NVIDIA GPU driver, DRA driver, and one NIC from the DRA net driver. And for the NIC, we are adding a selector to filter NICs that have the RDMA capability. In addition to that, the second section is about the constraints, the collocation constraint that we can set between these two devices, which means here that we are requesting both devices, GPUs and NICs, to be aligned via their PCI routes. This is the attribute that the resource slice exposed previously, and this means that we need to have the same value for this attribute in order for these devices to be collocated on the same PCI route. At the end, at the pod level or workload level, the resource allocation using DRA resource claims or resource claim templates is very simple. We can attach or reference the resource claim templates under the resource claim section, and this brings the physical constraint to be visible and schedulable with this workload spec. So the match attribute is a universal primitive. It means that these two devices requested previously needs to share the same value of the specific attribute that needs to be exposed by their DRA drivers. One thing about the hard constraint, this is not a soft or scheduling constraint. If the pod does not have, or the cluster does not have a node that satisfies this cluster, the pod stays pending. So when the requests of like creation of a pod with the DRA claim reach the scheduler looks for a node that satisfies the request. If it exists, it will bind the pod, creates the resource claim, and inject devices. This is deterministic allocation pattern. If the node does not exist, the pod will stay pending. So here, pending is honest. We can act on it, and there is no like silent degradation hidden behind our workload. One last thing here is how now we know how Kubernetes or like the schedulers select the devices. Now, how the correct devices end up in inside the container? The answer here is NRA, node resource interface. This is an extension point in containerd and cryo, which means that when a pod gets created with a DRA claim, the NRA plugin intercepts the container start request and injects the list of devices that the scheduler already picks and selected. And this means that the There is no hard coded values for the paths, device paths in your manifest. This can work in every node that has like enough resources available to satisfy the request. It's portable. Very quick example of a real use case where we have had this distributed multi-node disaggregated inference workload. At some point, our devices end up in different landed in different sockets, which means that the bandwidth, the transfer bandwidth between prefill and decode workers degrades significantly, and by enforcing the collocation between NICs and GPUs, the bandwidth jumped from 0.2 gigabytes per second to 40 gigabytes per second. Which is, with very simple configuration, we reached this goal. The final mental model here is that your hardware has its own topology map. The driver publishes this topology and your workload declares the requirements. And DRA here sits as a bridge to enforce collocation and allocation requirements. The old model was about counters and schedule and placements, and hoping that we end up with the right allocations. The new model declares the topology, scheduler enforces, and the performance is deterministic. Final takeaways. The scheduler is blind by default. Without DRA, we don't have any ways to, or any easy ways to express the topology. With DRA, topology is brought to the scheduling time, which means that we can act on it and we can make correct decisions. Match attributes is a universal primitive if we want to enforce some collocation requirements between your devices, and DRA is generally available in Kubernetes 1.34. Thank you so much for watching this presentation.